Alright, so we're going to have fun with partial fractions today. So today is partial fractions for the win day. Partial fractions are incredibly powerful because they allow you to take things that are complicated and weird looking and turn them into things that are happy. So partial fractions come up whenever you got something like, I don't know, like this. Alright, and wait, no, not with plus. Plus makes it bad. Let's go with the minus. And like, let's pretend you had to integrate it or do something else. Or maybe you're just looking at this from a college algebra perspective in which they say, just do partial fractions and don't worry about why you need to do it. But you do need to do it because one day you're going to have to integrate. Now, I can't integrate this on my own because this would be hard and scary, and I have to use partial fractions to do it, basically. So that's what we're going to do, is show you how to do that. Partial fractions comes from the basic idea that if I can rewrite something, say as factorable, x minus 1 and x plus 1, because I'm a factoring genius, that I can rewrite this, that there exists some, I don't know, some equation, some expression that is equivalent, and that expression is this. So basically, what this says is that if you give me 1 over x squared minus 1, that there exists in the universe this random expression where I don't have a squared thingy on the bottom. Okay, so that's partial fraction decomposition. So just take my word for it for a minute, and let me just kind of walk you through a little example to show you what it looks like. So basically what I've done is this is my leap of faith that this exists. And I'll tell you, I'm not going to tell you why we know it exists. I'll just tell you how to guess the right guesses. So basically we've got this going on here, and I want to figure out what A and B would make that statement true. Now to do that, I don't like fractions because they're scary. Even though this is partial fractions, it's still trying to do as few fractions as possible. So I'm going to multiply the entire thing by x plus 1 and x minus 1. So obviously, maybe, whenever I distribute this here, those cancel out, so I end up with just a 1. Then whenever I just take this and I distribute it here, the x minus 1's cancel out, and I just end up with a times x plus 1. Then, whenever I do this last little section, I've got b times the x plus 1's cancel out, and I just have x minus 1. Now, there's two ways to do this. There's kind of a hard way, and that's the first way I learned. And then there's an easy way, and when I learned the easy way, I was like, wait, why did I ever do it the other way? Okay, so basically the simple way is to make some lucky guesses and figure out what A and B are. Lucky guesses. So I'm going to say, what if I guess, and they're not really guesses, they're smart, strategizing, strategery, smart, I can't spell, S-M-A-R-T-E, smart, cleverness, I don't know, whatever you call it. So I've got smart cleverness here, and I'm going to say, what if x is equal to 1? Okay, because if this is true, then it has to be true for all values of x, right? Because that was my leap of faith, is that this is equal to that, and it can't just equal that for a specific value, it could equal that for all values, for x equals 0, for x equals 1, for x equals 882 billion. So what if x equals 1? Because it has to, eventually, for this to be true. So if x equals 1, I could say, well, then my equation becomes 1 plus a times, 1 equals a times x, which is 1, plus 1, plus b times x, which is 1 minus 1, right? So I've got 1 equals a times 2 plus b times 0, or 1 equals 2a, so a is equal to 1/2. Wow, I just found a. And I just found a because I was super, super clever. And by super, super clever, I mean I've done like a billion of these problems, and that's how you get to be good at them. All right, so I figured out a value for a. Now, I can also ask, what if x is equal to -1? Now, why did I choose -1? Because 1 just seems like something you'd accidentally guess. But the reason that the 1 worked out is whenever I look ahead, I say, wait, if I plug in a 1 here, this term is going to go to 0, which it did, and that's going to give me a almost directly, right? Does that make sense? So that means whenever I come over here, if I would like this term now to go to 0 so I can find b, I can say, well, if x is equal to -1, then that'll go away, and then I'll just have a value for b, which is what we do. So I'm going to come in here and I'll say, then that means that I'll have 1 is equal to a, x is -1 plus 1 plus b, and then x is -1 minus 1. And then I've got 1 is equal to a times 0 plus b times -2. So that's 1 is equal to -2b. So b is equal to -1/2. Now, a and b, like being the opposites of each other, that's just an accident. Just the way it turned out, it doesn't always happen that way. So, but here it does. So basically, now what I can do is I can go back up to my original statement, which is that 1 over x, and I'm just going to write it as x squared minus 1, is going to be equal to a, which is 1/2 over x minus 1, plus -1/2, which is b over x plus 1. So all I'm doing is I'm just coming back up to my original assumption, and I'm plugging stuff in. So, so if I want to rewrite this, I can say, well, anytime I see 1 over x squared minus 1, I can say that that is going to be equal to this. And that's really awesome. So if you're doing this because you want to do college algebra or because you want to do partial fractions, great. If you're doing this because you want to integrate, that's cool, because instead of trying to integrate this, which, oops, try to put that plus there, instead of trying to integrate this, which I don't know how to do, I could do the same thing as to integrate this, which is actually totally doable because those are just natural logs, and you don't know what I'm talking about, don't worry, just know that there's a reason that this is important, because it lets us do this.